This is Ms. Muturi, obviously, and I just want to remind you that before we do today's lesson, that tomorrow, well, actually today, the quiz on Castle Learning will open. So after you finish watching this lesson, please feel free. You can log on to your Castle Learning account and start the quiz. Remember, you will get one retake to earn credit if you are not happy with your initial quiz score. So what that means is if you take the quiz once and say you get a 75, but you want to aim to get an 85 or a 90, the same questions are going to be given to you in the retake, and it's just really up to you to put in that extra time and effort to get the highest grade that you're comfortable with for your quiz. So let's kind of get into our last lesson that will be included in your quiz, and that is volume of a cylinder and volume of a cone. So in our class, when we talk about a cylinder, it's always referred to that we are dealing with a right circular cylinder, not this oblique cylinder over here. This diagram might look familiar from when we did Cavaliere's principle. And just to quickly refresh your memory, Cavaliere's principle states if we have two solids that have the same heights, and at every parallel cross section their areas are the same, then the volumes will also be equal. So basically, how do we find, or where did the volume of a cylinder really come from? And like the stacking of the papers for the right prisms, I think of volume of a cylinder as stacking CDs. So basically, if you think of one CD as a circle, you can find the area of a circle using your formula pi r squared. But as soon as you start stacking those CDs, we add a third dimension of height. So once we add that third dimension of height, we now have a cylinder. Now a cylinder isn't a prism because we don't have rectangles around the outside faces, but same idea that the volume of the cylinder would come from taking the area of the CD and multiplying it by the number of CDs, or pi r squared times the height of the cylinder. So if we boil this down, really the volume formula for a cylinder is just pi r squared times the height, right? R is the radius of your circular base. H is the height of your cylinder. And this is just kind of the explanation in a little paragraph form if you want to take a second and read through it. So once we now have that formula, here it is, we can do some practice problems. So the problems for our cylinder, like this one here, are very straightforward. We have to find the volume in cubic centimeters based on this diagram. So we know that our diameter is 12, our height is 27, our formula is pi r squared times the height. So since my diameter is 12, my radius is going to be 6. So the 12 here isn't inserted into our formula. I have to take half the diameter to get the radius. Once I have my radius, I substitute it in, substitute in my height, and I look and I see pi in my answer, right down here. So that means in my calculator, I'm just evaluating 6 squared times 27, which is 972, and then I tag along pi. So it should be choice 3, 972 pi cubic centimeters. Number 2. So number 2 is a little bit of an application. It says we have tennis balls are sold in a cylindrical can with the ball stacked one on top of the other, which if you've ever gone to a sporting goods store, you've seen the tennis balls in that cylindrical can. And our tennis balls have a diameter of 6.7 centimeters. So to the nearest cubic centimeter, what's the minimum volume of the can that holds a stack of 4 tennis balls? So again, the tennis balls are in a cylindrical can. They have a diameter of 6.7 centimeters. What you have to think about is that a tennis ball is actually a sphere. So the diameter runs left to right, but also up and down. So what I did here was I kind of just sketched 4 tennis balls or circles stacked on top of each other. And I said, well, okay, if this is a sphere, here's my diameter, 6.7, 6.7, 6.7, 6.7. If they're stacked on top of each other, the minimum height has to be 26.8 centimeters because I added up the heights of all my 4 tennis balls. Now, if you're looking for the volume of the can, which is a cylinder, I just found the height. and that's 26.8 centimeters. But now I have to find the radius, and the radius is at the base. So here, across is like going across my sphere, or my circle, my tennis ball, and that's 6.7. But if I need the radius, I have to take half of 6.7, which is 3.35. So I substitute in 3.35 and 26.8. I look to see all of my answers don't have pi in it, so that means I'm evaluating this entire expression up here, and I want to round to the nearest whole number because all of these are round to the nearest whole number, and I get 945 cubic centimeters. All right, moving on now to a cone. So a cone is similar to the pyramid in that it kind of comes up here to this little point. But what's different about a cone is that a cone relates to a cylinder. So how do we find the volume of a cone? So the volume of a cone is actually 1/3 the volume of a cylinder, which is pi r squared times the height. To reiterate, like the pyramid, there's a height of your cone, or the altitude, and the slant height, along with a radius. But we know that in this little triangle here, the slant height and the height, or the altitude of the cone, are two different numbers. I know that because when I connect all three, I form this right triangle, and the slant height acts as the hypotenuse of that right triangle, so it always must be the longest side. So slant height is always going to be larger than the height of your cone. Slant height can sometimes be represented by this script L. Just to go through the derivations quickly, the derivation of the cone, two different methods. The stacking method, which is like the stacking of the cubes for the prism versus the pyramid. Again, kind of starting with a base of the same size, same height. As we increase our base, we see that the volume approaches that number of 0.33333, which is 1/3. So if we compare the volume of a cylinder to the volume of the pyramid with the same size base and the same height, eventually we'll kind of come to the conclusion that the cone is 1/3 the volume of the cylinder. Personally, I like the pouring method. So the pouring method is like the pouring method of the prism and the pyramid. We start with our two solids that have the same size bases and the same heights. One's a cylinder, one's a cone. If we fill the cone up with sand, water, anything, and we pour it into that cylinder, we see that one pour gets us 1/3 of the way. Two pours, 2/3 of the way, and 3 pours, and we have our cylinder completely filled. So that means that the volume of a cone is 1/3 the volume of that cylinder. All right, so let's just try a couple of questions dealing with the volume of a cone, and we have our formula right here, and see how it goes. So first question, it says a cone has the volume of 108 pi, and a base diameter of 12. So right away, once I know my diameter is 12, I kind of fill in that I need the radius of 6. What's the height of the cone? So I start with my formula. Volume equals 1/3 pi r squared times the height. My volume is 108 pi. My radius is 6. The height is unknown. Make sure that if you see pi in the answer for your volume, you need to include it when you substitute it in. So our volume is 108 pi equals 1/3 pi 6 squared times the height. Okay, from here, remember, it's just semantics about algebra. How are you going to get the height by itself, h by itself? So I evaluate up here. I take 1/3 of 36 to get 12, bring down my pi and my h. Now to get h by itself, I'm going to divide by 12 pi, so your pi's cancel. 12's cancel on this side. 108 divided by 12 is 9, so your height is 9. We don't have any units, so we're just going to say our height is 9 units. Choice 2. Okay, next page, number 2. So for number 2, what we have here is a cone and a cylinder. It tells us a little bit about the cone that has a radius of 3 inches. The slant height is 5 inches. So remember, slant height, although that's good to have, it's not what we need in order to find the volume. The cylinder has a radius of 4 and a height of 6. We have to determine and state the full number of cones needed to completely fill the cylinder with water. Okay, So basically what we need to do is find the volume of both and then see how many of these cones does it take to fill up the cylinder. So before we can find the volume of this cone, we have to figure out the altitude or the height of the cone. So I turn this into my right triangle. I have A, B, and this hypotenuse is C. I plug it into Pythagorean theorem. I evaluate and I find that the height of the cone is 4 inches. So now that I have all the information, I have the radii of both as well as the heights, and here it is. So my cone is 1/3 pi r squared times the height, my radius and my height. I leave it in terms of pi, it's just easier to deal with. So the volume of the cone is 12 pi, while the volume of the cylinder with the radius of 4 and height of 6 is 96 pi, right? Two different formulas because one's a cone and one is a cylinder. So how many cones will it take to fill up the cylinder? Anyone, if you kind of just take a second and think about it, how to figure it out, what would we do? And what we would do is we would take the volume of the cylinder and divide it by the volume of the cone. That tells us how many cones fit inside of a cylinder or how many cones would make up that cylinder. And we get 8. So we know that it will take 8 full cones to completely fill that cylinder. And that is the answer there. Okay, and that's the last question for volume of a cone and volume of a cylinder. Remember that quiz through Castle Learning is now open. It will be open until May 4th at 9 o'clock a.m. You will get one retake to earn the best grade you feel like you want to earn. If you have any questions, email me using that little white envelope on my eBoard page, and I will get back to you as soon as possible. Hope you all are doing well, and enjoy your weekend.